So the title of my presentation is Autonomous Navigation and Inspection for Smart Cities. I'm Professor Myung from KAIST Korea. Can you see these animations? So let me explain these animations later. Oh, thank you. So can you see the letter URL on the top right side here? Here. So these are the students from our lab, and our lab's name is Urban Robotics Lab. Yeah, we are aiming at developing the robotics technologies for smart cities. We are focusing on robot navigation technologies combined with AI and machine learning, and we are developing a lot of vision and LiDAR or different sensor-based SLAM technologies, and also we integrate the deep learning for semantic navigation. And also we make some drones for autonomous flight, and swarm robotics is another research area in our lab. And for smart city applications, we build low-cost self-driving cars, and Keros is the climbing aerial robot system for inspection of the structures, and Feros is the fireproof aerial robot system for scouting in the fire disaster situation. And the last topic is the environmental robotics. We have built the jellyfish removing robot called Zeros, and oil spill protection robot, green energy removal robot, and finally the Morbot, which will be introduced later in more detail. Our lab focuses on developing SLAM technologies featured by the graph-based sensor fusion for dynamic and feature-pro environment. So to cope with dynamic environment, we can remove the force constraints by forming the GP SLAM or G2P SLAM dynabins, which will be introduced later. And we can improve the SLAM performance by using the local sensor fusion technologies. So this is the first technology we have developed, GP SLAM, for enhancing the SLAM for low dynamic environment. So we first group the nodes based on the covariances of the nodes, and then we prune the force constraint based on some metric for the grouped nodes. And this video will show how it works. So we extract the features from the environment, and we form the graph. And also you can see the nodes and the constraints in the graph. And if somebody moves the environment, like some objects, then the robot in the conventional SLAM, it fails like in the red lines, yellow lines. But our method, GP SLAM, can build a graph and build a 3D map exactly, as you can see. And this is the general version of the GP SLAM called G2P SLAM. We can deal with the multiple low dynamic objects, and also we can deal with the nonlinear paths, and we can remove high and low dynamic objects in the environment. Maybe this can be played.
Experimental environment shown as figures.
Can you hear the sound?
First, let me show you the group generation demo.
Maybe.
Black colored nodes are ungrouped node, and the same colored nodes represent that they are in the same group.
Sound is muted.
The remote part can hear it.
No, can hear?
But
Okay,
it's not
okay.
broadcasted in the room. So.
Yeah, that's good.
Exactly.
Okay. So
as you
we
can
form
see,
the group,
groups are correctly generated.
The same color
Next,
indicates the
matching
same group.
process are
And
shown.
once we see the loop closure situation, then you can see that if the object is slightly moved, then we can remove some dynamic object from the environment, and we can actually build the static 3D environment like this way. And also we can incorporate deep learning for identifying some objects from the environment. For example, in this situation, the human is recognized using the deep learning, and we can eliminate those point clouds from the human. And using the static point cloud map, we can plan the paths and can command the robot. This is the static 3D map of the environment. and we can navigate. If the human is obstructing the robot, then the robot can avoid the human by recognizing the human. And we have also built the GPICP, which is benefiting from the ground vehicle. So the conventional ICP is vulnerable to some errors in the matching. So we limit the search space for matching within the similar height for the ground vehicle. So by introducing this GPICP, you can reduce the complete time and also enhance the success rate. As you can see, we have succeeded, but ICP, generalized ICP, fails in this situation. And we are also making self-driving vehicle. In our lab, we installed the RTK GPS and 3D LiDAR and 2 RGB cameras and ION. And we are generating the HD map, high definition map, using the augmented features like the planar features from the building and pole-like features from the tree trunks or some pole-like objects. And also we can extract the curve features from the environment. And we can integrate all these features to the original high definition map. So you can see this video. Yeah, we extract the features from the environment. Sorry. So in real time, you can extract the planar features, pole-like features, planar features, or the curve features like this way, and we can localize the vehicle quite accurately. So you can compare the result with the RTK GPS. They coincide with each other. And this is the localization part. And we actually can build a map like this way. We can actually build a map about 4,000 times smaller map can be built compared to the usual 3D point cloud data. And then to build this 3D map, we can utilize our graph-based SLAM method in the environment. So once we have the loop closure, then we can optimize the graph and build a 3D point cloud map like this way. So this is the actual autonomous driving at our campus at KAIST. So we can extract the features from the environment like this way. Some trunks or some building features are extracted, and by using that, we can localize the vehicle and drive autonomously. So we should cope with the low terrain in the construction site. So we are also developing low terrain navigation technologies. So we have developed the travel, which is the traversable area detection algorithm. So you can see that we have the blue parts, which indicates the traversable area. And you can also compare the magenta line, which is the result from RTK GPS, and the cyan one is from the proposed localization method. So this is a little bit bumpy and slopey area. So in spite of this situation, we can drive the vehicle autonomously. So this will be presented in IROS 2022. So let me skip the detailed explanation. The features in this algorithm is that we are using the tri-grid field, which is castellating the space using the triangles, which can yield the smoother traversable area and smoother paths. So what happens if we have the feature pro environment? In that case, we cannot use the vision or LiDAR sensors properly. So we have come up with the idea to use the anomaly of the Earth's magnetic field. So this will be used as the features in the indoor or underground situation. So in most of the indoor environment, there are steel frames. So using the anomaly of the magnetic field due to the steel frames, we can localize the vehicle. So, but if you just use the magnetic field in one spot, that may be very ambiguous. So we try to use the sequence of magnetic fields to match the nodes. So this is the result for indoor environment. So you can see that we have the sequence of magnetic fields, and if you have a loop closure situation, then they will be matched. So in here, we have the loop closure situation, so we can minimize the error like this way. So you can compare in the right side, we have the SIG LiDAR. You can see the cyan color from the SIG LiDAR and blue color from the optimized pose graph from our method. So they actually coincide quite closely. So we have tried to use this method for underground SLAM. So in the underground situation, we don't have any data available using the vision or the LiDAR sensors. So we have tried to use the magnetic sequences, and by matching two magnetic sequences from two IMUs, from front side and the rear side of the vehicle, we can match them and have the SLAM technologies on here. So we have developed
The
the
mole
ball
bot imitated
which
moles
mimics
which
the
can move freely
behavior
under the
and
ground.
anatomy of the moles.
Let's take a deeper
Maybe
look into the mole bot,
on the remote
which
side,
can perform
you can
various
hear
tasks,
the sound,
including
yeah.
powerful excavations.
So we can dig the underground up to 4
저희가
megapascal,
개발한 두더지 로봇은
and
두더지의 생물학적인
we
구조
can
그리고
incorporate
생물학적인 습성을
our
이용해서 그 굴착
magnetic
할 수 있는
sequence-based localization method.
The mole bot imitated moles which can move freely under the ground. Let's take a deeper look. Thought to exchange
We have
signals
locally
wirelessly
implemented the
in a
localization
confined
system for
underground
like
space.
here.
And the research team apply the location recognition
By
system
recognizing
it has
the,
developed to the
position in
robot.
the underground, we can command the vehicle to go the destination.
여기에 보이는 화면은
to dig
두더지
up
로봇을
here.
움직이기 위한 소프트웨어입니다. 이 소프트웨어를 통해서 드릴링, 앞발의 움직임, 로봇의 움직임을
The mole
And we have further tried to implement visual inertial odometry, and we incorporated the line features for enhancing the visual odometry. So actually, by combining the line features in the indoor situation, we can decrease the RMSE up to 16% compared to SOTA algorithm. And this will be also presented in this conference called UV SLAM, unconstrained line-based SLAM. And we actually incorporate the line features, and we add the vanishing point detection algorithm, and then we incorporate this one as the residual to the original cost function. And the result is that we can obtain more neat structural element, as you can see. We can compare the previous result on the left side. And by analyzing the feature information matrix, we could confirm that our state estimator can result in the full observability. And we are also incorporating VIO for quadrupedal robots like this way. So this paper will be also presented in this conference. So we incorporate the pre-integrated full blast vector. This will be added to the original graph optimization algorithm. And usually the conventional optimization method incorporates non-slip assumption for the legs. But in this algorithm, we don't have such kind of assumption. So it is quite robust for slippery conditions. So the details will be heard in the conference. So let me skip quickly. So we have applied our algorithm for mini cheetah platform. So this is the gravel area, so it is quite slippery, and we could achieve the best performance compared to the state-of-the-art Pronto algorithm or Bin's fusion algorithm. And the next topic is for maintenance and disaster prevention using the structures monitoring techniques. So we have tried to use the UAVs for bridge inspection. So we incorporate VIO with the 3D LiDAR, and we proposed HSLAM, hierarchical graph SLAM. So this is the combination of the GICP and some kind of Bin's algorithm and some NDT algorithm. So this is the platform we are using. So incorporate the monocular camera with the 3D LiDAR and IMU and DSLR camera for high resolution images. So we had a field test in 2 bridges in Korea. So this is the first site. You can see we can build the 3D point cloud map as well as estimating each state. So in the underneath the bridge, we don't have the GPS signal. So this is quite challenging situation. We can build this 3D map autonomously. And this is the second site. And by installing the DSLR camera, we can capture the high resolution images for the underneath the site of the bridges. And finally, we can get all these 3D point cloud maps, and also these high definition maps, images can be obtained by analyzing those images. We can know where is the crack area, and we can also know the exact position of the crack area. We can compare our algorithm with the ROM and REO mapping. So this is the quantitative result. So the proposed method outperforms the others, and RealSam especially failed in the second site. So to cover that structure, we should incorporate the coverage path planner. So we have proposed multi-layer coverage path planner for large structures. So we first generate the prior map, and then we generate the viewpoint, and then we have the path planner using the TSP solver, and viewpoint can be resampled, and finally we can complete the coverage. So this is the algorithm explanation. So we split the structure layer by layer, and we first have the initial sampling, and then we use the TSP solver to optimize the paths at here, and these are the updated viewpoints. So this will affect the second layer. So in the second layer, these sampled points will be moved slightly. And again, if we proceed this way, we can cover all the area. So this will be the result. This is the Big Bang from UK, Big Bang model. So we can slice the vertical structures like this way, and we can build a coverage path planner like this way. Actually, this can be applied to any kind of structures, whether it can be vertical or horizontal. We can split into the vertical and horizontal parts at first and learn the MLCPP for horizontal part, and then learn the same algorithm for vertical parts, and we can connect all the paths like this. And then this is the 3D point cloud map we have obtained using our coverage path planner, and using some offline algorithm, we can obtain these colorized 3D point cloud maps. So we have tried to use our platform and algorithm for seaside structures, seaside bridges, and in that situation, there is a very strong wind. So sometimes it is hard to harbor around. So we have come up with the idea to use the drone. So this drone can fly and also perch to the wall of the structure and have the closer inspection.
Here at the
So
Urban
this
Robotics Lab in KAIST,
drone
researchers
can
are
attach
developing machines
to any
work
kind of
in
structures
unusual
like the
places.
marble walls or
We've seen a lot of
the
drones
brick
here on
walls.
site, but never actually one that can climb a wall.
like here. So at first, we have the macro inspection. And if we find some spot to be inspected further, then we can push to the structure and have the micro inspection. So this is the actual shot of our carrots. So it is slightly windy situation. So once it touches to the structure, then it's very stable. And we can have the closer look into the surface of the structure. We can apply these carrots to various applications like scouting in the fire disaster situation, and also we can clean the glassy walls like here. So this unit. So this drone can endure up to 1,000 degrees Celsius up to 20 minutes using the aramid fiber surrounding this drone. And we can also use our wall climbing capability for inspecting the narrow spaces. So this drone can be applied to various applications like cleaning the walls or cleaning the solar panels, inspecting the airplanes. So this is the recent version called Keros Q. We have the multi mid-air pose change and fail-safe mechanism installed in this Keros. So you can see we have the tilted rotors, and you can change its pose in the mid-air. So it does not have any impact to the surface of the structure. So we also have the cleaning mechanism. And in case it fails the power, due to the power shortage, we have the fail-safe mechanism. So we attach the suction cup to the surface, and we have some tether. And after cleaning this structure, we can detach this suction cup and go to the original position. Okay. So in conclusion, there are a lot of challenges for future construction. We have to deal with the long-term autonomy. So we have to deal with the dynamic environment and weather daylight changes. And we should perform SLAM in diverse environment. This is actually far from the industry standard, I think. GPS denied environment and feature pro environment should be dealt with. And we should recognize the roof closures for large-scale structures or large-scale areas. We can also use the deep learning or machine learning-based approaches. And multi-level SLAM is another good research area for future construction, I think. Thanks for your listening. Okay.